Welcome to this artificial intelligence module related recording. This module will form one part of the CS160 course, and this particular recording will walk you through an example that uses an artificial intelligence / machine learning system to make predictions about the prices of homes in California. And your CS160 instructor will get into details related to some of the concepts we'll be touching as part of this recording. But there are a couple of key ideas that I want you to keep in mind before we get going. So first, on your screen, you should be seeing an Excel spreadsheet that represents the housing data set that we'll be using as part of this recorded machine learning / artificial intelligence example. And our housing data set will be used by the machine learning system to create a paradigm that will allow it to predict the prices of homes in California. Now, our housing prices predictor will in particular be using an AI / machine learning process called supervised learning. In supervised learning, we feed data to our machine learning system in order to train it to identify patterns in the given data set that it can then use to make future predictions. Now, let me repeat this because it's a very, very important idea. In supervised learning, we feed data to our machine learning system. So in our scenario, we'll feed this data set to our machine learning system in order to train it so that it can identify patterns in this data that will allow it to make future predictions about home prices in California. Now, just to emphasize the importance of understanding this idea of supervised learning, I'm going to switch screens and show you maybe a couple of slides on supervised learning. And so this first slide is a generic definition of machine learning. And what is machine learning? Well, one simple way of thinking about it is that it's the science of programming computers so that they can learn from data. And this comes back to what we spoke about a couple of minutes ago, i.e., we will feed our machine learning system data, for example, in our case, a housing data set, so that we can train it to detect patterns in the data, which will allow it to make effective future predictions about house prices in California. So at a high level, machine learning is the science of programming computers so that they can learn from data. And a simple example that might resonate with you is an algorithm that learns to detect spam emails by looking at large sets of examples of regular emails. So think about you training a machine learning system on how to detect junk mail or spam by exposing your machine learning system to hundreds of thousands of emails that you've received in the past. And you can label your emails as being junk or not junk. And based on the training that your machine learning system receives by looking at the historical emails, it will then in the future be able to predict whether an incoming email that you receive, whether it's junk or not. Okay, so again, machine learning is the science of programming computers so that they can learn from data. Okay, now I know that your instructors in CS160 will be talking more about supervised learning and unsupervised learning and reinforcement learning, but I just wanted to show you this one slide that relates to supervised learning because it's directly tied to what we'll be doing in this video with the housing data set. So what is supervised learning? Well, in supervised learning, the training data that you feed to your machine learning algorithm includes the desired solutions called labels. So let's step back and break this sentence down. The training data that you feed to your machine learning algorithm includes the desired solutions. Well, think about that spam email detector example that we just discussed a minute ago. In that scenario, you're feeding your machine learning system training data that has labels, the labels being whether the email is junk or not. And if you expose your machine learning system to hundreds of thousands of historical emails that include the labels, then you're training your machine learning system to detect patterns in the data that it can then use to, in the future, predict whether an incoming email is junk or not without being given the answer. So again, supervised learning is a very, very important conceptual idea and one which we'll be using in the housing data set example. That's a topic that we'll be covering in this video recording. Switch back to the housing data set itself. Let me switch sharing here. And let's talk about how we would approach the process of creating a machine learning predictor or machine learning prediction system. And as far as possible, I will avoid getting into the weeds and be very sparse in my usage of technical jargon. I'll try to keep things at a high level so you can understand the concepts without getting lost in complex technical verbiage. Okay, so with all that said, this was just setting up the lecture recording. Let's take a look at the housing data set that we'll be working with. I just took a sip of water. So what you're seeing here is the Excel spreadsheet that lays out the key features of the housing data set. So if you look at the first column here, it says longitude. The second column is latitude. What does that do? Well, these two features allow you to isolate the location of the house. So now I've already told you that the house is in California, but even if I had not, you could have used the longitude/latitude values to identify the location of this particular house. Right? So the longitude and latitude features allow you to isolate the location of the house in this particular data point. And I think we have 20,600 odd data points in this particular housing data set. Okay, and then we have this housing median age column. And this is a feature that gives you the median age of the family living in the house, give the total rooms in the house. And this has to be divided by the total number of houses in this area to get the average number of rooms in individual houses. And then total bedrooms is another feature. So the 5 features that we looked at so far: longitude, latitude, housing median age, which means the median age of the family living in the house, the total rooms in the house, the total bedrooms in the house, the population of the area in which the house is located, the number of households living in this particular location, the median income of the family living in this particular house, and we'll have to scale it by 10,000 to get the median income in thousands of dollars. And then you have the median house value itself here in column I. That's another feature. And then the ocean proximity feature. Now, let's just pause and think about what these features are telling us. So these features here: longitude, latitude, housing median age, the total number of rooms, the total number of bedrooms, the population of the area in which the house is located, the number of households in this area, the median income of the family living in the house, the ocean proximity. All of these features are useful in being able to predict the price of the house. And what's that value? What's the column that holds the price of a house? It's the median house value column. This here is our label in our supervised learning paradigm. These are the answers that we are feeding to our machine learning system in order to train it, right? So what we'll do is we will train our machine learning system by feeding it these 20,000 odd data points. And these data points will include the answer that we are training our machine learning system to predict in the future. And the answer in this case is the median house value. So these are our labels in the supervised learning lexicon. And don't worry, we'll go over supervised learning. Your instructor will go over supervised learning in more detail in class. Once you understand this, let's think about what are the steps you need to take in order to build a machine learning system. So remember, in this particular example, we're going to use these features: longitude, latitude, housing median age, total rooms, total bedrooms, population of the area, number of households in the area, the median income of the family living in the house, the ocean proximity of the house. We'll use all these features to predict the price of the house, i.e. the median house value. And so step one in any process that is intended to build a machine learning system is to eyeball the data set that you're going to be working with. Just get a feel for what the data set is all about. So that's what we've done here. We've taken step one, which is to just quickly glance at our raw data set and try to understand what the data set is all about, what the features are that will allow you to train your machine learning system to make predictions about a particular value in the future. In this case, the predictions that you want your machine learning system to make in the future is the median house value. Now I'm going to switch again. I'm going to switch screens again. And I'm going to use Word to explain a concept that many of you must have seen in high school, which is this idea of linear regression. We'll start with a multivariate linear regression example, and then we'll look at the univariate example, single variable linear regression example as well. And my goal here will be to keep things as simple as possible. So don't get overwhelmed by the jargon. And we'll go with this example in class as well. Your instructor will go with this example in class as well. So if you have questions after watching the recording, you can always bring up your questions in class. Okay, so how are we going to use the data we have in the housing data set to train our machine learning prediction paradigm? So two things. Number one, remember in supervised learning, we feed our data set to the machine learning system in order to train it. And what do? So in our case, let's say we have 20,656 data points that are 20,656 data points. Each represents a home in California. Yeah. So what we'll do is this. We will use 80% odd of this 20,656, or let's make it even simpler. How about I say I'll use 16,000 of these data points to train my machine learning system. Train, let's call it ML system. Okay. And then the remaining around 4,656 data points, I'll set them aside for our testing. When we finish training our machine learning system, we will use these data points to test the efficacy of our trained machine learning system. And I'll talk about this in more detail in a couple of minutes. But for now, remember, we'll be training our machine learning system on 16,000 of the 20,656 data points in our housing data set. But what does training mean? Remember, if I go back to my Excel spreadsheet, remember when I spoke about the spam email detector machine learning system? I told you that you would be feeding your machine learning system hundreds of thousands of historical emails from the past, and you have one column in those emails that labels an email junk or not junk. And so you train your machine learning system on those hundreds of thousands of emails that includes the label, i.e. whether the email is junk or not. And so in the future, when you give a new email to your machine learning system and you don't include the label, i.e. you don't give it the answer whether the email is junk or not, your machine learning system is able to predict whether that email is junk or not based on its training. In our case, what we'll do is we'll feed 16,000 of these data points to our machine learning system, and we'll include the answer, which is the median house value. That's what we're trying to predict in the future. When we train the machine learning system, we give it the answer. It gets trained on all these features and the answer, and then in the future, I'll give it a new house. I'll give my machine learning system a new house. I'll give it all these features, 1, 2, 3, 4, 5, 6, 7, 8. So longitude, latitude, house, median age, total rooms, total bedrooms, population, number of households, median income, proximity. I'll give it all these features, but I will not give the now trained machine learning system the median house value. And this machine learning system should be able to predict what a house's median house value should be based on these features: longitude, latitude, median age, total rooms, total bedrooms, population, households, median income, ocean proximity. Okay? So that's the training part of the supervised learning driven machine learning system. Okay? Now, how does this work? So let's go back to our Word document. Let's talk a little bit about that. So when you think about your machine learning system, what you're given is the features, and let's call the features x1, x2, x3, up to xn, right? So each one of these values is a feature of your data set. So this could be median age of the family living in the house, right? This is one feature, x1. x2 could be the median income of the family living in the house. Okay. x3 could be the ocean proximity feature. All these are features of your housing data set. Each house in your housing data set has these features. And in order to be able to make a prediction for the price of house, the equation we'll be using is this. Y, let's say y hat, is equal to theta 0, x0, plus theta 1, x1, plus theta 2, x2, plus theta n, xn. What does this mean? Well, we already know what these x1, x2, xn's are, right? So these x1, x2, xn stand for the features of your housing data sets. X1 could be median age, x2 could be median income, x3 could be ocean proximity, so on and so forth, up to n. And in our case, we have n equals to, I think, 8 features. Now, your real world data set might have up to 100 features. So n can be equal to 100. But that's what these x's stand for. Now, what are these thetas? Theta 1, theta 2. Well, these are the weights you assign to the features. So depending on how critical a feature is in allowing you to predict the price of a house, you assign a weight that's commensurate with how important a feature is in allowing you to predict the price of a house. That's a lot of words. So let me give you a clear example. So when we looked at the correlation function in step 2 of our machine learning process, we noticed that the housing median income, the median income of the family living in the house, is a strong predictor of the price of the house. So there's a very strong correlation between the income of the family living in the house and the price of the house they live in. So what would I do? I would assign a higher weight to that feature. So if x1 is the median income feature, then this theta I would assign to x1 would be very high. Now, let's say that the population of the area in which the house is located does not have that high an impact on the price of the house. Well, in that case, I would assign a smaller weight to that feature. These thetas are the weights you assign to individual features, right? And so this equation here, and for now, let's just focus on the theta 1, x1 plus theta 2, x2 plus theta n, x. And I'll come to theta 0, x0 in a second. But this is the equation you use to make a prediction for the price of the house. Okay. Now, let's talk about the theta 0. So as I mentioned, we'll be working with linear regression. So think of this as your x-axis and this is your y-axis. And this theta 0 is the point at which your prediction line hits the y-axis, or the y-intercept. This line is in linear regression paradigm. In a linear regression paradigm, is called as the best fit line. And again, we'll break down in very simple terms what linear regression does in a second. But this theta 0 is just the point at which your prediction line, the line that holds all your housing value predictors, that line intercepts the y-axis at theta 0. And again, let's simplify this process. What does it mean in our housing data set example to say that the y-intercept is this point, theta 0? Well, it means that, let's say the minimum base value of a house in a particular location is 50,000. So then this theta 0 would be 50,000, which means that at least a minimum price that you're setting for a house in a particular area is 50,000. There are no houses less than that. That's your base. Now, if you wanted to start at 0, you could just have the y-intercept not be at 50,000. You could start this line here. So then in that case, right here, you'd have your y-intercept here at 0, which means that there is no minimum base value. The minimum base value is $0. But let's say in our case, we start our housing price value at 50,000. That's our y-intercept, or theta 0. The x0 is just a term we use to make the computations a little easy, and x0 is always 1. Now, why do I say we use this to make the math easier to work with? Well, because what you're seeing here is you have multiple variables. And so what you're seeing here is an example of what's called multivariate regression. And in order to simplify this, what we do is we use something called vectors. And many of you must have seen this in linear algebra in high school. So here you have your x equals to x0, x1. So x is a vector of this form, xn. And then theta is a vector of this form, theta 0, theta 1, theta n. Yeah? Okay. So if you have these vectors, then you can simplify this y predictor to be something like this. You can say y hat. Also, you might see this verbiage this symbol, h theta of x, is equal to theta transpose dot product of x. Now, this simplifies our equation. And so that's why we are using the x0 here in order to simplify the math. When I open this theta transpose, for example, if I take the transpose of this vector, what do I get? I get theta 0, theta 1, theta 2, theta n. And then x is, of course, x0, x1, x2, xn. So this opens up to this equation here. Okay? So I have shared this with you in order to show you in simple terms the equation that we use to make a prediction in a machine learning, a linear regression machine learning algorithm. But what we'll do is we'll simplify this so that instead of using n features, I'll just use one feature. The feature that is most critical in predicting the price of a house in California. And as you, I'm sure, already know, that's the median income of the family living in the house. So instead of using n features, I can just use one feature. Just use one feature, y theta equals to theta 0 plus theta 1 x1. But the x1 is the median income of a family living in the house, right? And if theta 0 is 0, let's say start at the y-intercept is at 0, then you have y theta equals theta 1 x1. So that's a very, very simple equation for you to work with. Now, one other thing I'll quickly mention before we transition to looking at the machine learning code in Python, if we think about just using one feature, which is the median income, then this x-axis is just your median income, and your y-axis is the prediction you're making for the price of the house. And so this best fit line will have all these data points, which are your predictions, right? And let's say these are the actual values of the houses. Let me use a different color here, probably, or at least use a smaller font for the data points. So these are the actual values of the houses in California. These are predictions. And what you're trying to do is you're trying to minimize the distance between your predictions, which are these on these lines, and the actual values. That's what you're trying to do with your machine learning prediction system. Yeah. Okay, so I know some of this would seem a little overwhelming at first, but I promise you it's fairly easy, and I've tried to stay away from technical jargon as much as I could. But now let's switch to looking at the machine learning Python code itself. I think some of this will make more sense once you look at the machine learning code itself. So I'm going to switch screens again. I'm going to go to Google Colab and to show you the Python source code. Let's new share, and let me come to the Google Colab screen. And we're there. So I'm going to open a new notebook, and that is called, and all of this code will be shared with you, the machine learning regression algo. Okay, so it's still loading, but in a second, you'll see the code for the machine learning prediction model. Oh, there it is. Okay, so let's walk through this code together. Yeah. Most of this is fairly straightforward, and I think, firstly, two things I guess I should highlight. One is your instructor will go over this code in more detail in class, and two is the code might look intimidating at first, but as you work with it, it'll get fairly straightforward, and you'll be able to better understand the instructions. But for now, in this particular video recording, I just wanted to highlight a few things. In this line here, you're uploading your housing data set. This is exactly the same thing you did when we looked at the Python code that allowed you to create charts to better understand the housing data set and to create the table that gave you the correlations between the features of the housing data set. So this is exactly the same thing. Okay. Here you're just saying simple machine learning algorithm, nothing new here. Here, what I've done is I have removed all the features in the housing data set other than the median income. Now, the median income is the feature that is most influencing the price of a house. We saw in our correlations table that 68.8% of the price of a house can be explained by the median income of the family living in the house. So median income has an inordinate impact on the price of a house. So in order to simplify our machine learning prediction system, I've removed all the features from our machine learning algorithm except for the median income. So here I'm uploading our data from the housing data set that's related to median income, and of course the label, which is the median house value, which we're trying to predict. Yeah. So as I had explained to you in the example that we discussed on the Word document on the Blackboard, we will split our data set into a training segment and a testing segment. So training is when you train your machine learning system to be able to make predictions, and the testing data points will be used to test the efficacy of our now trained machine learning system. So that's what this is doing. We have the training samples and the testing samples, the training labels and testing labels. Yeah. And you can look at this code more closely offline, all of this code will be uploaded to D2L. And as I have said incessantly during this lecture recording, your CS160 instructor will also go over this code with you in class. But here's the part that I want to focus so that you can relate what you're seeing in this code to what I showed you on the Word document on the blackboard. So here's the instruction that allows you to work with linear regression. Remember that chart I showed you? Let me switch screens here again, in case you've forgotten. Remember this best fit line I showed you? This is the linear regression pictorial, and this is the best fit line. And so we are using linear regression in our machine learning system, and this instruction here allows me to use linear regression in my Python code, this line here. This just gives me an instance of a linear regression object that I can use to train my machine learning system on the given data set. And so the next line here is basically training your machine learning system. It's giving it the samples and the answers. Remember, in the training part, you give it all the features of the house along with the answers. So I give it not just the housing median income, i.e. the median income of the family living in the house, but also give it the price of the house. So I'm training it. And then once the system is trained, then I'll use the testing data set to test to better understand the efficacy of my now trained machine learning. That's a lot of words, and I know sometimes, even though I'm trying hard to stay away from technical jargon, sometimes it's unavoidable. But I'll summarize this in layperson's terms by saying, think about this program as enabling you to train your machine learning system to be able to predict the price of a house. And these lines here are doing the training. And this line here, the first two lines, are allowing you to actualize the training of your machine learning system, especially the line which fits the data. And then this line is allowing you to make predictions, the predictions line, linear-reg.predict. Okay. And then finally, two things I guess I should say quickly. It's not just enough to make predictions about the price of a house that you give to your machine learning system, i.e., let's say you find a great looking house in Beverly Hills, California, and you want to know the price of the house. So you enter the data into your machine learning system, you give it the median income of the family living in the house, and then your machine learning system should be able to predict what the price of that house should be. But it's not just enough to have a machine learning system that makes a prediction. You then have to have a way to validate the efficacy of the prediction that your system makes. And that's what this error criterion is doing. We're using something called root mean square error to identify the error in our machine learning system's prediction. And I'll switch back to Word for a second to relate this to something we spoke earlier. Remember I told you earlier that if this is your best fit line, this is the line that has all your housing price predictions, and these are the actual values of the houses, and you want to minimize the distance between your predictions and the actual values. You want to minimize that delta. And that's what this error function is doing. It's trying to measure to see what's the delta between your prediction and the actual price of the house. So let's pick that house we spoke about in Beverly Hills, and you feed the features of that house to your machine learning system, and it makes a prediction for the house. Let's say it predicts that house is $500,000. Then what you'll do is you'll find out what the actual price of the house is, and the delta between the actual price and the predicted price should be really small. That's what you want in your machine learning prediction system. The prediction you're making should be as close as possible to the actual value. And you measure the efficacy of a system by using some error function, which in our case here, in this example, is a root mean square error. And that's what this line is doing here. Yeah. And then the next two lines are just basically creating that linear regression best fit line that I showed you in the Word document. Okay. So when you run this code, you get, this is your output. And so these are your training samples, these are your testing samples, and this is your prediction for the house. And this is we're predicting the first 5 houses. We're predicting the price of the first 5 houses in the testing sample of the housing data set. And the error here is 84,710. That's the error between the average error between your machine learning system's predictions and the actual prices of the houses in the testing section of the housing data set. Yeah. And this here is the picture. It's the pictorial version of what we are looking at here in numerical form. So these are all the actual price of the houses, and this line here has your predictions. And as you can see, it's not optimal, but it's fairly good. The best fit line is going right through the predictions of the price of the houses. So delta is fairly small. It could be better if you look at it carefully. It could be better. You could have a line that could be more optimal because you have an error which is around 84,710 average error that your machine learning housing price prediction system is making. And so it could be better, but it's still in the vicinity of what the actual housing prices are, i.e. your prediction line, your best fit line is still in the vicinity of what the actual housing prices are. And in future lectures, we'll look at how you can use something called backpropagation to optimize your machine learning system and reduce this error function, i.e. minimize the error value. But for now, I hope that this description of how you can build a machine learning system has been useful. Let me just summarize the 3 steps you'll be taking regardless of which machine learning system you build. Step 1 in your machine learning predictor building process is to eyeball your data set. Just look at the raw data set. Let me switch screens here. Just look at your raw data set. In this case, we looked at the housing data set and get a feel for what the underlying data is telling you. What does this data set represent? At step 1. Step 2 is to then use Python, i.e. the Python programming language, to better analyze the data set. Use charts, use the correlation function to better understand what the underlying data set is telling you. And in our case, it told us a few things. It told us, number 1, where the population density is the highest in California, and that's a good indicator for house prices. The more dense the population in an area, typically the higher the house values. And then this was telling you exactly where the housing prices are the highest at this point. And then this gave you a pictorial representation of the correlation between different features in your housing data set. And then once you realize that there's a strong correlation between the price of a house and the median income of the family living in the house, you then created the scatter plot that plotted median house value against median income. So the second part of the machine learning prediction builder system, the second part that you want to focus on is to use Python to analyze your data set in a more efficacious way, in a more effective way, in a more optimal way. And you're using charts and using correlation functions to do that. Okay? And then finally, the third step in the process of building an efficacious and effective and optimal machine learning prediction system is to write the code that will actualize the machine learning prediction paradigm. And that is right here. I'm going to open up the notebook that has the code for that, which is in our case, the machine learning regression algorithm. And what that does is it gives you some predictions for housing prices and then tells you what the error is, the average error is in the predictions made by your machine learning system and the actual prices of the houses in California. And then this chart here is a picture that represents the best fit line, i.e. it represents your predictions and the delta between your predictions, which are on this red line, and the actual values of the houses in California, which are these blue dots. I know, even as I wrap up this video, that for many of you, this information might seem overwhelming. My suggestion to all of you would be take some time, play with the code, go through the 3 steps I outlined, and you will see that this process is actually fairly seamless. And your CS160 instructor will go over each of these concepts in great detail in class as well. Okay, with that said, I want to thank all of you for listening to me and for watching this video recording. Hopefully it was helpful. And if you have questions, please do follow up with your CS160 instructor. Okay, thank you so much.